Welcome. This is Lecture 10, Part 1. We're continuing our examination of markets, though now what we're going to look at is an exchange economy where we're not producing goods, but we have a certain amount of goods out there distributed between individuals. Can we use a market to find a way to make those individuals better off? And generally this goes under the concept of efficiency, and specifically when we're looking at this distribution of resources, Pareto efficiency. So what we're going to look at is an exchange economy that has two individuals. There are two goods out there distributed between the individuals, and we'll think about ways to redistribute the goods to make both individuals better off. The key concept here is the idea of Pareto efficiency. And an allocation is Pareto efficient if I cannot rearrange the goods to make one person better off without making the other one worse off. And so obviously a distribution is not Pareto efficient if I can rearrange the goods so that I can make both people better off. What we want to do is we want to keep redistributing the goods till I get to one of these Pareto efficient outcomes. I can't make one person better off without making the other one worse off. We can use some of the concepts that we know about the consumer, and specifically our knowledge of utility functions, to see what makes someone better off or worse off. If utility goes up, then the person's better off. If utility goes down, the person's worse off. So let's consider an economy where there are two goods, two people. The two goods are good X and good Y. The two people are person A and person B. Without knowing anything about the distribution, we can write the well-being and draw the well-being of the two individuals using their utility function and then their indifference curves. So for person A, we'll have a indifference curve map. For person B, we'll have an indifference curve map. The key idea that links person A and person B is that whatever person A does not have of good X, person B must have, and whatever person B does not have of good Y, person A must have. So the quantity of good X that person A has, XA, plus the quantity of good X that person B has to equal the total amount of good X in the economy. Similarly, for good Y, the amount that person A has, YA, plus the amount that person B has, YB, has to equal the total amount of Y in the economy, YT. So I can look at those two utility maps again and notice how the two individuals are linked. If, for example, person B does not have any of the two goods, so the amount of good X and the amount of good Y that person B has are 0, 0, 0 of each, we're at the origin, well, that must mean that person A has all of the two goods, so has XT and YT of the two goods. Similarly, whatever amount that person A has, say X1A, person B must have whatever's left over, or XT minus X1A, and that will represent by X1B. And that will also be true for good Y. So whatever person A has, Y1A, person B just has what's left over, and we know that the two amounts add up to the total. And so what happens if we make a redistribution? So let's say, for example, we give person A more of both good X and good Y. So person A moves from that initial X1A, Y1A to the green dot that's further out, both in the horizontal and the vertical direction. Because the total does not change, person B's distribution must be a reduction of both. And the black arrow that shows the movement for person A has to be exactly the same arrow in reverse for person B. Whatever we give to person A in good X has to be exactly the amount that we take away from person B. And whatever we give to person A in good Y has to be exactly what we take away from person Y. And I can see from this example already that if I give person A more of both goods, then I must be making person B worse off. This is not a situation where both are being made better off. I can also see that it's possible to have a redistribution that makes both person A and person B better off. Obviously, this involves having more of one good and less of another. I can't give one individual more of both and have the other one also be better off. But if, for example, I gave person A more of good Y and less of good X, remembering that the trading line for person B has to be the exact same line in the opposite direction, it's possible for person A to move to an indifference curve that's farther away from the origin, and for person B to also move to an indifference curve that's farther away from the origin. And that's going to depend a little bit on the shape of the indifference curves. Person A's indifference curves are a little bit flatter than person B's, so person A can move up and to the left, and person B can move down and to the right, and they can both be better off. We're measuring whether you're better off by whether you're on an indifference curve that's farther away from the origin than the initial one. So what we want to do is we want to figure out whether we can keep moving to other points that would make each one better off. It would make perfect sense that if they could redistribute the goods so that both are better off, that they would do that. There's no damage to either one. And it's difficult to see when we have the two graphs separate. So what we're going to do is we're going to use a trick. That trick's called an Edgeworth box. And the advantage of the Edgeworth box is that we'll put both of the indifference curves in the same diagram. That will allow us much more easily to see when both are made better off, or when I can't make one better off without making the other one worse off. Where are those Pareto efficient points? So the insight to use the Edgeworth box is going to be to notice that the line segment 0 to xt in person A's diagram is the same length as the line segment from 0 to xt in person B's diagram, and more importantly, that there's a one-to-one relationship between the values between 0 and xt in person A's diagram and the values from 0 to xt in person B's diagram. Is that as person A's diagram goes from 0 to xt, person B's diagram goes from xt to 0. So if I could find a way to put person B's diagram on person A's diagram, noting that instead of going from right to left, 0 to xt, person B's values go from right to left, I'd be in pretty good shape. And the trick then is going to be to rotate person B's diagram 180 degrees. So what I've done is I've kept person A's diagram as it is, noted the maximum values of X, the maximum values of Y, XT and YT, and then rotated person B's diagram 180 degrees. The origin, instead of being down and to the left, is up and to the right. So just think about rotating a piece of paper 180 degrees. Person B's origin is up and to the left. Person B's indifference curves, instead of being increasing, going up and to the right away from the origin, they're increasing, going down and to the left away from the origin. Person B's origin is 0. XT is XT units to the left. YT is YT units down. That's exactly what we want to be able to look at person A and person B together. So this is really important. Make sure you understand this rotation of person B's diagram by 180 degrees. But once you see that, you'll see that the units are matched up exactly right. The size of the box, XT units of X, YT units of Y, are the same in the two diagrams. What goes from 0 to xt in person A's diagram goes from xt to 0 in person B's diagram, and we can put the two diagrams on top of each other. So the Edgeworth box has dimensions xt and yt. Any point inside the box divides up the good X and good Y between the two individuals. So, for example, if I take an endowment point, the black dot that I've got drawn there, person A has from 0 to the x value of that point coming from the person A's origin, and then person B has the x value going from its origin in the top right to xt moving from right to left in the Edgeworth box. Any point in the box divides up the two goods between the two individuals so that the total amount xt is perfectly exhausted. So now I can see that in contrast to the situation when I had two separate indifference curve maps, it's fairly easy to see when a redistribution will make both better off. If I can move to a point that's on an indifference curve farther away from person A's origin or up and to the right, and also to an indifference curve that's farther away from person B's origin down and to the left, then both will be made better off. Simply, if I draw the indifference curves that go through the endowment point or any other point that I'm looking at, if those indifference curves intersect, there has to be an area between them where a redistribution to that area will make both better off. So if I look at that red arrow that I've got drawn on the diagram on the slide, I move up and to the left, I'm moving to a point that's farther away from the origin from person A, and on an indifference curve that's farther away from person B's origin. Anytime that there's room between the two indifference curves, I can move and make both better off. How long can this process go on? And the insight is that anytime that there's any daylight between the two indifference curves, I can move into that space and make both person A and person B better off. So the only time that I can't do that is if there's no space between the indifference curves. Well, we know what that is. That's when the two indifference curves are tangent. And so when the two indifference curves are tangent, I cannot make one person better off without making the other one worse off. Well, we've already said that those are what are called Pareto efficient points. So when the indifference curves are tangent to each other, I have a Pareto efficient point. When I connect all of those Pareto efficient points, I have what's known as the contract curve. The contract curve is the locus of points that are Pareto efficient. Since the individuals will always move from a distribution that's not Pareto efficient to one that makes them both better off, they eventually will trade to a point on the contract curve. If we start from a particular endowment, like my endowment point that I have here, which points on the contract curve make both better off? Well, the contract curve goes all the way from person A's origin to person B's origin when we don't know what the endowment is. But once we see what the endowment is, there's a limited number of points on the contract curve that could make both better off. Person A wants to be on an indifference curve that's farther away from the origin than the indifference curve at the endowment point. Person B wants to be on an indifference curve that's farther away from its origin than the endowment point is. Person A wants to move up and to the right. Person B wants to move down and to the left. Only the blue highlighted points on the contract curve would make both person A and person B better off. How do we find those points? Well, I know the equation for the indifference curve for person A, whatever the utility is in the endowment point. I just plug that into the equation for utility to find the equation of that indifference curve. And similarly for person B, I can find the point on the contract curve if I know the equation of the contract curve. I'll have two equations, two unknowns. It's on the contract curve. It's on the indifference curve through the endowment point.